Swayam Prabha. Digital India. Educated India.
Welcome back. Today we are going to look into complex numbers and phasors in a bit more detail. See, the thing is, last class what we saw that suppose I take sine of omega t as reference, right? So I can show it as a vector of magnitude 1 and parallel to the x-axis. So now suppose I have something which is sine of omega t plus phi. So then I can show it as a unit magnitude vector at an angle phi. So if I have something which is a sine omega t plus phi, then I have to just scale it up by this much, scale it up by the length a. I am assuming a to be greater than 1, and this becomes the vector. This is the representation of a sine omega t plus phi. If you had taken cos of omega t as reference, then this 1 angle 0 vector parallel to x-axis on x-axis would represent this vector, in which case cos of omega t plus phi would be represented by this unit vector, and a cos of omega t plus phi would be represented by this vector. So it is not very this representation of sinusoids at a fixed frequency is not dependent upon whether you take sine omega t as a reference or cos omega t as a reference. But once you take either sine omega t as a reference or cos omega t as a reference, throughout your session, throughout your problem, throughout your theory, whatever you are developing, you should stick to that itself as reference. You don't have a liberty to change the reference midway through. That liberty you don't have. You have liberty to choose sine omega t as a reference or cos of omega t as a reference. Now, if you are suppose doing a vector addition like this, then what we have shown in the last class, that first, I mean, this is not a vector addition, this is addition of sinusoids at same frequency. This same frequency is again something very important. All the phasor arithmetic that we are developing, it means all the sinusoids are at the same frequency, typically 50 hertz for us, 60 hertz for United States, like that. But this frequency is not changing. That's why we are able to do the phasor arithmetic. You cannot like create a phasor at 50 hertz and add it with a phasor at 100 hertz. That's simply not done. Please, I mean, I have discussed this earlier also in the class. phasor addition or vector addition, vector representation of addition of sinusoids can only be done provided all the sinusoids correspond to same frequency. So, suppose I want to do this, then what did I tell you last time? I told you last time that you can take this as the phasor A, and I am showing right now, if you notice, I am showing the amplitude of the sinusoid as the length of the phasor or the vector, and angle of the sinusoid as the uh, what do you say, angle from the x-axis. So let me just change this color so it's not so this is the thing. Now the next one, b sine omega t plus phi, is, let's say, be this. So notice that angle is always shown in the anti-clockwise direction. And then what do? We do this parallelogram law of identity. We complete this parallelogram, and the resultant vector here, is the vector sum of the vector a plus b. And why is it so? Because what you are doing is, if you notice the way I did it, I just lifted this vector b from here, moved it parallel here, placed it at the tip of the a vector, and the head of the a vector, the tip of the a vector, and so this became the b vector. So this is the a vector to which I added the b vector. Then geometrically, this, the new tip of the b vector, and the origin is the vector a plus b. Also, we discussed that day that this is same as taking first of all the projections on the x and y axis. First project a onto y axis. So this becomes a sine phi a. Now this b vector, project this b sine phi b. So you can see that the resultant vectors A's projection onto x-axis is, so a plus b's projection on x-axis is a cos phi a plus b cos of phi b, and a plus b's projection on y-axis is a sine phi a plus b sine of phi b. So by parallelogram law of identity, which we are by the Pythagoras theorem, which we are going to apply on this right angle triangle. So for that, so let me call this as point O, A, and say B, just for the sake of it. So the resultant O A square is equal to OB square plus AB square, and OA square is A cos of phi A plus B cos of phi B whole square plus A sine of phi A plus B sine of phi B whole square, and so this is A square cos square phi A plus sine square phi A plus B square cos square phi B plus sine square phi B plus 2ab cos of phi a cos of phi b plus sine of phi a plus sine of phi b, but being cos square theta plus sine square theta being 1, this is a square plus b square, and cos a cos b plus cos sin a sin b is cos of a minus b. So therefore the length finally OA square, or the I'll write it as the square of the resultant is this. So the resultant vector will have a magnitude of a square plus b square plus 2ab cos of phi a minus phi b, and let's say this angle is phi, the resultant makes an angle of phi, then tan of phi is AB by OB. So therefore tan of phi is A sin phi A plus B sin phi B divided by A cos phi A plus B cos of phi B. So this is the way to do this is the way to apply parallelogram law of identities. And then, since we were doing something in the time domain, our question is actually what is the resultant in the time domain. So therefore the resultant in the time domain is going to be given by, I am going to write the complete thing just for the sake of completeness for you, 2ab cos of phi a minus phi b into sine of omega t plus phi, which is tan inverse of okay, so I think better I will write it compactly, it's getting too lengthy. So it is the resultant r times sine of omega t plus of phi, where the phi is worked out as tan phi is worked out as above, so phi is tan inverse of it. You should be careful about the quadrants. If the numerator is in the positive, I mean if this is positive positive, phi will be in first quadrant. If this is, so I'll write it like this, if the this is numerator, this is denominator, if numerator is positive and the denominator is negative, then the phi will be in second quadrant. Why? Because the denominator represents x-axis. So x-axis has, let me draw the four quadrants here. Let me draw a vector in the positive, this thing. So the both of these are positive positive. Now suppose the vector is in the second quadrant, then what happens? The y-axis, which means the numerator, is positive and the denominator is negative. And if you go in the third quadrant, then both are negative. So this is also minus minus, means phi is in the third quadrant. And if you are in the fourth quadrant, then this is the projection on x-axis, this is the projection on y-axis. So I'm sorry, I have written it the other way, right? Numerator denominator. So yx numerator denominator. So both numerator and denominator are positive, then it is in first quadrant. If the numerator is positive, that is projection on y-axis is positive and projection on x-axis is negative, then it is in the second quadrant. Both projections on x-axis and y-axis, if they are negative, it is in the third quadrant. And if the projection on x-axis is positive and the projection on y-axis is negative, then it is in the fourth quadrant. So if I just say tan phi of minus 5, then there is a ambiguity in it. It could be minus 5 by 1, it could be 5 by minus 1, which will change the quadrant in which it is there. So please be careful when you solve vectorial problems not to equivalence this by minus 5. Whenever I say minus 5, I actually would mean this. I won't mean this. So even though both of them are minus 5, it is very important to keep track of this. Similarly, if I say 5, 5 can be 5 by 1 or it could be minus 5 by minus 1. But minus 5 by minus 1 will bring the resultant vector in the third quadrant, while 5 by 1 will bring it in the first quadrant. So please again be careful about this particular fact, and what is whether the real part is positive or imaginary part is positive. I have actually stepped forward when I have used this word imaginary part, so I'll be coming back and connecting it to it very soon. But locating the quadrant is very important. So therefore, whenever I write tan phi, please write the correct signs for the numerator and denominator so that you can place the vector in the right quadrant. And once you have placed the vector in the right quadrant, then you can apply this and rewrite the algebraic form of the the time domain representation of the sinusoid. So essentially what we are saying is phasor addition of vectors and phasors. I mean, in electrical engineering, because they represent phase quantities, we call them as phasors, but otherwise they are vectors only. Their addition and subtraction can be abstracted out through so sinusoids at same frequency, at same frequency, their addition and subtraction can be abstracted out by vector addition and subtraction, which is less tedious, much easier, and subtraction. And once you have done that, this is what you are doing it, then you can rewrite the equation back in this in the sinusoidal form and get your answer again back in time domain. So therefore these phasors essentially are phasor representations are essentially transformations. You can go from time domain to a vector domain and do your work there and return back again in the time domain. Why should you go into the vector domain? Because it is more convenient. That is the whole reason that we are doing that as this thing. And then we did one application in the last class where we solved a series RLC circuit using we were looking at the steady state response of this particular thing, and we said that we can take I to be equal to Im sine of, we showed in fact that this fits the bill. So I can write, when I substitute this here, I can take Im common and I can write this as R plus L di by dt will be so the derivative of sine of omega t plus phi is omega cos of omega t plus phi. So I will write this as, I'm sorry, so RIM sine of omega t plus phi plus omega L IM cos of omega t plus phi minus 1 by omega c IM. Again, the integral of cos is going to be, sine is going to be minus of cos. So, and integral is cos of omega, integral of sine of omega t is minus of 1 by omega cos of omega t. So, therefore, this becomes plus equal to phi. So, I can take IM common, right? This is sort of a bit of repetition, but I am doing it because it is important in my opinion to get a good understanding of what is happening. You get something like this, and then we said that okay, let us keep r on the x-axis, let us take omega L minus 1 by omega c on the y-axis, let us call this resultant as a vector z, let us call this resultant as vector z at an angle theta. Then I can write r as z cos theta and omega L minus 1 by omega c as z sine of theta. And so I divide and multiply this by z, and I can write this as cos of theta sine of omega t plus phi plus sine of theta cos of omega t plus phi. So sine A cos B plus cos A sine B can be written as sine of A plus of B. So therefore this can be written as sine of omega t. This is sine A, this is cos B, this is cos A, this is sine B. So this is sine of A plus B, which is phi plus theta, and this should be equal to, this should be equal to what? What is the our right hand side? Vm sine of omega t. So this should be equal to Vm sine of omega t. So therefore Im will be equal to, this is multiplying and dividing it by the magnitude or the length of the vector z. So this is Im is Vm by z amperes, and sine of omega t plus phi plus theta is same as sine of omega t, implies phi should be equal to minus of theta. So therefore the current response is going to be equal to Vm by z sine of omega t minus of theta. Now, is this not very simple and convenient? What only thing that I have to do is, given a series RLC circuit like this, I just need to calculate its net impedance, and the magnitude of the net impedance is R square plus omega L minus 1 by omega c whole square under root. And so you can think of it as R on this, omega L minus omega c on the y-axis, and magnitude of z as this, and look at this angle theta. So this is called the impedance triangle. This is called as an impedance triangle, and you look at the magnitude of this angle theta, and you got the impedance and the theta. So what you are doing is, to get the peak amplitude of the current, just divide the peak amplitude of the voltage by the corresponding impedance magnitude, and then get the angle of the from the impedance triangle, angle of the impedance, and right now create a lag. This minus of theta is to be interpreted as lag as lag in the phase, and create a lag of minus theta in the sinusoidal response. So if the voltage phasor is Vm sine of omega t is represented by this phasor Vm, then the current phasor I of t is represented in magnitude by Im here, which is Vm by magnitude of z, and an angle of minus of theta. So clockwise go. Now instead of going anti-clockwise, go clockwise and show this as minus of theta. So this basically gives you the current response, sinusoidal current response. Now in this implicit is that I have assumed omega L to be greater than omega C, greater than 1 by omega C. This is what I have assumed. That's why this thing has come out to be positive. Such a circuit in which the omega L dominates 1 by omega C is actually said to be an inductive circuit. It looks more like an inductive circuit, L being the inductance. But suppose it is equally possible that 1 by omega C, C is very small, so 1 by omega C dominates, L is small, so 1 by omega C dominates omega L, in which case this term will become negative. So actually it will be somewhere here, and so the theta angle will turn out to be negative. The theta angle will turn out to be negative, in which case this minus of minus will become positive, and so you will get a circuit which is having a in which the current is leading the current is leading the current is leading the voltage phasor. So let me first draw the lagging one just to show you, to bring out some clarity, and maybe I'll do a simple. I have done directly an RL. It will be easy now for us to do one RL. I have directly done a RL and a RL. I have directly done a RLC, but now it will be easier for us to specialize it to just an RL or just an RC. We will do it once. This is this is my theta, this is the current response I of t, this is the V of t, this should be my Vm, this should be my Im, and when I say the current lags by an angle theta, so suppose this theta is 30 degrees. So suppose if I say that my current lags by an angle of 30 degrees, then what I mean to say here, so I'll write this axis as omega of t, because if I just write it as t, then the angle will I will have to say that 2 pi corresponds to the time period t. So or 360 degrees corresponds to time period of t. So 1 degree will correspond to t by 360 in time, and so 30 degrees will correspond to 30 divided by t by 360, which is t by 12. And so everything I will have to keep doing this kind of proper calibration in t, and then mark it on the x-axis. Instead of that, it may be just better to take x-axis, the time axis, in terms of omega of t, the omega of t, so that when I can say theta is 30 degree, I can just go back here and draw 30 degrees, a lag of 30 degrees, offset of 30 degrees, and draw the waveform. Now the lag of 30 degrees, therefore here what it means, that the rising zero edge of the current phasor is delayed by t by 12 seconds. So for 50 hertz waveform, capital T is like 20 milliseconds. So 20 milliseconds divided by 12, whatever that number is, it is less than 2 milliseconds, obviously. It is delayed by the corresponding rising edge of the zero crossing of the current waveform is delayed by p by 12 of the seconds with respect to the rising of the current. And so the going down zero is also delayed in the same way. The rising peak is also delayed in the same way, and the reducing other way around is also delayed in the same way. And even though I have shown it here only, I'm sorry, even though I have um, shown it in the first quadrant only, but one should remember that all sinusoidal responses will happen from t going towards plus infinity to t going towards minus infinity. So it is a steady state response of the circuit. And as I said earlier, all the transients in the previous class, as I mentioned in the last class, all the transients have decayed down. This is something important that we are assuming. No, actually, there is nothing like t towards minus infinity. Most of the time, we are only interested in what happens in future. But analytically, it is important to understand that when we are talking of the steady state response, what we mean to say is, if we look back also, we are expecting the same phenomenon to be repeating in the past. And now, though we are more interested in what is happening in the future, the same phenomenon, periodic phenomenon, is happening in the past also. With this, now let us just do let us now do a RL circuit, sinusoidal response of an RL circuit. And then so for a change, I will take this now as cos of omega t. Okay, I'll take this as cos of omega t. For your sake, first I will write down the differential equation. Now, if I have written it as Vm cos of omega t, immediately it should click to me that it would be better to take cos of omega t as reference. There is no point now to say that I want to force sine of omega t as a reference. It is okay now directly to take cos of omega t as the reference. The moment I say this, what I am trying now to say is that I will take the current response as cos of omega t plus phi. Now this is what I am going to take, and I substitute it here. I don't have to, I can generalize it very quickly, but this is a class, so I am going to do that. And then when I differentiate d by dt of I, where I of t is taken to be Im cos of omega t, then this is going to be omega L Im cos will become minus of sine derivative of phi, which will be equal to Vm cos of omega t. So take Im common, take impedance triangle, draw R here, draw omega L here on the y-axis, complete the Z, call this angle as theta, and now divide this by Z, divide this by Z, multiply this by modulus of Z, take Im common out, and now write R by Z as cos of theta, cos of omega t plus phi, minus sine of theta. Omega L by mod of Z is going to be sine of theta. So sine of theta into sine of omega t plus of phi, and then this can be written as cos A cos B minus sin A sin B is going to be equal to cos of A plus of B. So therefore cos of omega t plus phi plus of theta, and this should be equal to Vm cos of omega of t, the applied voltage to this circuit. So therefore, clearly Im is going to be equal to Vm by mod Z, and again theta will be, phi will be equal to minus of theta, and the current response is going to be Vm by mod Z cos of omega t minus of theta. So suppose again the theta turns out to be 30 degrees. The ratio between omega L and R is such that tan of theta is 30 degrees. So sin 30 degrees is half divided by cos 30 degrees is root 3 by 2. So this is say 1 by root 3. So all we are saying is the ratio of omega L by R, the ratio of omega L by R is of the order of 1 is to root 3. Then it doesn't matter, means if it is 2 omega L 2R, also the angle will be 30 degrees only, or it is 0.5 omega L corresponding value and 0.5 R corresponding value, even then the ratio will be 1 by root 3 only. It is only on the ratio of and proportion between the omega L part and the R part. The omega L is actually called as reactance. As I said, reactance, impedance, these are all words of similar meaning to resistance, but the resistance word, so to say, has already been taken by the resistance. These are showing similar phenomenon, so we are calling them as omega L as reactance, and the combination of net effect of reactance and resistance, we are calling it as impedance. But the whole idea is following from the Ohm's law, that the voltage divided by resistance is current. So here also the net effect of R and L impedes the flow, and that impedes the flow. In DC it resists the flow. Here we are saying it with only resistance it resists the flow, and therefore we call the current is, we use the word resistance. Here it impedes the flow, so therefore we use the word impedance. And this 1 by omega, so 1 by omega L is called actually inductive reactance, and 1 by omega C is actually called as, it's also reactance, but it is called as capacitive reactance. 1 by omega C is also called as capacitive reactance. And I will leave it to you to check that the dimension wise, the dimension of omega L should be ohms, and dimension of omega C again should be ohms. Okay, let me do it. Let me do it for L. For C, I will leave it to you. That's the dual element. So remember, V is equal to L di by dt. So therefore, what is the dimension of L? The dimension of L is, this means that L is V divided by di by dt. So dimension of this is V divided by ampere per second, or in other words, volt second by ampere. So this is the dimension of L, which is basically the Henry. Now what is dimension of omega L? So dimension of omega L is going to be, omega is 2 pi by t and L is V divided by ampere inverse. 2 pi has no dimension, so this is 1 by second. 1 by t dimension is 1 by second into V divided by ampere per second, so ampere second inverse. So this is nothing but V by ampere, which again by dimension comes out to be ohm. Similarly, I leave it to you to check that the dimension of 1 by omega C is also ohms only. It is also dimension wise, it is also ohms only. So that means it tends to resist. I am trying to sort of give you that feel but the resistor is a dissipative element. Inductor and a capacitor, a pure inductor and a pure capacitor are not dissipative elements. They store energy, they release energy, they can take the energy back, they can release the energy back. They are more like energy storage elements, and the resistance is more like a dissipative element. You should think of your geyser, for example, in your home, or a incandescent bulb. These are pure resistive elements, and with inductances you should think in terms of magnets or magnetic electromagnets, and for capacitances, of course, you have to think in terms of the dielectric capacitors, the two plates, and that you have seen in your physics class. Okay, now let's do quickly. Okay, now one more small point. If I say that the current is voltage is say 1 angle 0, and the current is, let's say, 0.5 and lags by an angle of 30 degrees. So I can directly say this is the volts, this is the net current. I mean, this is rather the phasor. So being phasor, let me show it like this by a vector, the net current. Usually for phasors we use capital letters, for instantaneous values we use small case letters. This is a normal convention, and when I want to emphasize that it is a vector or a phasor, I am also putting an arrow, but in general I don't need to do it, because all instantaneous values I am going to show it by small letters, and all phasors I am going to show by show by the capital letters. And wherever I use the subscript m, like V of m or I of m, it means the amplitude of the corresponding sinusoid. So now in this case, what is the impedance? So the impedance is 1 at an angle of 0 and 0.5 at an angle of minus 30 degrees. So this is 2 at an angle of 30 degrees. Now I am already doing complex arithmetic, even though I have not really explained to you how I do complex arithmetic, but it's so intuitive that you can pick it up. I will be giving you more justifications as I go forward. And this is the impedance is going to be in ohm, and so this is going to be 2 cos of 30 degrees plus the imaginary part. Now that I am writing it as a I am writing it already as a complex number, I am going to use Euler's identity straight away and write it like this. But I am going to come back and go deeper into this, so that you should not feel the disconnect. And so this is 2 root 3 by 2, and j is shown to be the imaginary number, the square root of minus 1 times of half, and so this will become root 3 plus j of 1, which is to say that r is root 3 and omega L is 1, or actually all I know is 1 by omega c 1 by omega c minus 1 by omega L minus 1 of omega c is 1. So what I am trying to sort of say is, if I give you just a response, so you have a black box, you connected a CRO, you saw what is the voltage waveform, you saw what is the current waveform. You can immediately tell what is going to be the net impedance, the Z. But from that you cannot tell whether there is only inductor or there is an inductor or a capacitor also sitting in the black box. Resistive part you can see it is there, but from there alone you cannot say whether it is a RL circuit or a RLC circuit. Now let us take a RC circuit. Again, I am only interested in the sinusoidal response. I am going to write it now again as Vm sine of omega t. This is capacity C, this is the I. So my equation is going to be 1 by I minus infinity to t, I of tau, t of tau is equal to Vm sine of omega t again let me presume that I of t is equal to I of sine of omega t plus of phi. Then I will get R of Im sine of omega t plus phi plus 1 by omega of c cos. When I differentiate cos sine, it becomes cos. So I will when I integrate so when I differentiate cos, it becomes minus sine. So when I integrate sine, it will come as minus of cos of omega t plus phi. This will be equal to Vm of sine of omega t. And now let me take Im and z common, and this is going to be R. This is because it is minus 1 by omega c, so I am drawing it the other way around, and this is going to be my theta. So I am going to take this as z. So again I am going to divide it by z and multiply and divide it by z, and take Im also as common. So z times of Im, R by modulus of z, I will write it as cos of theta sine of omega t plus of phi minus 1 by omega c by the modulus of z will be sine of theta into cos of omega t plus of phi, and so this is going to be equal to mod of z times of Im sin a cos b minus cos a sin a cos b minus cos a sin of b. So sin of a minus of b. So sin of omega t plus of phi minus of theta. And so so in this particular case, the theta is negative because it is in the fourth quadrant. So the theta is negative, and this should be also equated as Vm sine of omega t equal to mod of z of Im sine of omega t plus of phi minus of theta. And so we get that Im is going to be equal to Vm by mod of z, and theta should now phi should become equal to theta. But since I have drawn it correctly, here it is 30 degrees. So this theta, for example, would be 30 degrees. And so I of t will become Im of sine of omega t plus of phi, which is Im of sine of omega t. For example, if it is 30 degrees, will be sine of omega t plus 30 degrees. So the point what I am trying to sort of say is, in a capacitive circuit, current leads the voltage. We have already seen that in an inductive circuit, sinusoidal current lags the voltage. Now let us do a series parallel RLC circuit. I'm sorry, just let's do a RLC parallel circuit. So I have Vm sine of omega t applied here, and my interest is in finding the current response. What is the current response? What is the I of t? So the same voltage whatever I have applied here, the same voltage comes here, V of t. So the I of let's call this as IR of t, let's call this as IC of t, and let's call this as IL of t. So in this case, I of t can be written as, by Kirchhoff's current law, IL of t plus IC of t. Is that right? And for IR, we can just write it as Vm sine of omega t by R, because V of t is same as Vm of sine of omega t by R. And for IC of t, I'll first write IC of t. It is, what is IC of t? C dV by dt. But what is my V? It is Vm sine of omega t. So therefore I will write it as Vm omega c cos of omega of t. So I'll write this as Vm omega c cos of omega of t. And now let us come to the IL of t. So we know that VL of t is L DIL by current in the inductor being IL, L di by dt is equal to VL of t. So therefore the IL of t can be written through integration process as VL of t dt, I'm sorry, VL, I should use auxiliary variable tau here. So VL of tau d tau from minus infinity to t and 1 by L of that. So if you recall, Vc of t we had written as 1 by c. This is the dual of exactly this equation. I of, this is just the reciprocal or the dual of this equation. So L and C are like dual elements in the electrical engineering. Now what is the why did I bring it out here? Because this is the net charge which has accumulated from minus infinity to plus t, and that net charge divided by the capacitance is the net charge divided by the capacitance is the voltage. Similarly here, this is the net flux which has accumulated, the net flux linkage which has accumulated from minus infinity to t, and flux is equal to L times of I. So that divided by the inductance is gives me the inductive current. So now I am going to write the third quantity here for IL of t as 1 by omega L, and sine cos differentiated is minus sine, so integrated will be sine integrated will be minus of cos, omega will come down, cos of omega of t. And so if you simplify this further, you can take first of all Vm common out and then write it as 1 by R. So 1 by R, let me call it as G. The reciprocal of the resistance is the conductance G, plus G times of sine of omega t plus omega c minus 1 by omega L and times of cos of omega of t. Now the reciprocal of reactance is called susceptance, So what was the capacitive reactance Xc? This. So reciprocal of this is this thing. So unit would be reciprocal, unit of resistance reciprocal will be Siemens, which is 1 by basically ohm, also sometimes called as mho. All of them are basically, mho is basically ohm spelled the other way around to indicate that we are talking of reciprocal. And Siemens is a name of a scientist, so 1 by omega c, Siemens incident is also very important company in electrical engineering. So 1 by xc will be omega c. Similarly, XL we had seen was omega times of L, the inductive reactance. This is the capacitive reactance. Reactances are usually showed by X, resistances by R, impedances by Z. And so 1 by omega L is going to be the capacitive 1 by XL. This is 1 by XL, which is the reciprocal of the so this is BL. The susceptances are shown usually by a symbol B. I don't know why, but they are shown by G and B. So you get the, if 1 by omega L is shown by BL and omega C, the capacitive reactance is 1 by omega C. So just omega C is the reciprocal of the capacitive reactance, that is shown by B of C. Now, so if you look at it, actually, when I have in parallel circuit, say a resistive circuit, 3 resistors in parallel, and I ask you what is the net resistance, what do you say? You say take reciprocal of each of the resistances, add all the three of them. Suppose there were 3 such resistances, take the reciprocal of each of the resistances, add of them, then take the reciprocal. So R1 equivalent will be 1 by R1 plus 1 by R2 plus 1 by R3, and that is the, whatever you add, that is the reciprocal of the net resistance. And so then from get the net resistance from here. Something very similar is happening here again with the RLC circuit. So what we have taken is reciprocal of the resistance here, we have taken reciprocal of the capacitive reactance here, and we have taken the reciprocal of the inductive reactance here. And the inductive reactance had come with a positive sign, this has come with a negative sign. The capacitive reactance had come with a, in the series circuit it had come with a negative sign, that has now come with a positive sign. So even the signs have gone through a reciprocal thing. And now this thing here, what I am going to do is, I am going to write this as Vm into 1 by R. So I am going to write it as simply as G sine of omega t, and by taking omega c minus omega L common, I am going to call this as the B, and I will write this as B times of cos of omega of t. And now you can see that what I should be doing, I should be creating a right angle triangle with G and B, and this should be the square root of G square plus B square, which is called as the admittance. In reciprocal of impedance is called as admittance, and its symbol is Y, just I think a preceding symbol to Z. And so I am going to divide this by magnitude of the admittance, multiply it by the magnitude of admittance, so as to keep everything proper and intact. And then this will be called, let's call this as theta. So cos of theta sine of omega t plus sine of theta cos of omega t, and so y times of Vm sine of omega t plus of sine of omega t plus of theta. So I think I have so this is what I have got here. And what is this? No problem. What is this? Left hand side is, this here I am. So this is nothing but I of t, IR of t plus IL of t plus IC of t. And so I have directly, without doing any further equivalencing, I get I of t. So I again see that it is a sinusoid, and in this particular case the current is going to be the magnitude of the current is going to be uh, Im is going to be mod of y times of Vm. So unit of this is volts, a unit of admittance is 1 by ohms, so therefore amperes, and in this case it is going to lead by an angle. There I had said it will lag by an angle theta, here I am saying that it will lead by an angle theta. I think we will take a break here. Thank you.